Welcome to Metabolic's open mic session at the Disruptive Innovation Festival. We're really excited to be here because the DIF, the Disruptive Innovation Festival, is all about bringing people together to talk about the economy is changing, what do I need to know and what do I need to do. We're pleased to be part of that because we believe at Metabolic that we do need to make some fundamental shifts or some disruptions, if you will, to move towards a more sustainable economy. And the way we work actually is by knowing and doing. So those two things are very important. So know and do, give advice, take action. One major change in the economy is obviously the circular economy. Eva's going to talk a bit more about that in a second. But within that, there's obviously quite a lot to discuss. So we're really going to zoom in today on resource use, and again, a large topic. So we're going to look at how it's very simple to take an oversimplistic view of this, and therefore it's quite dangerous and we miss all the opportunities and actually don't make the change we need. So today, the subject of the talk is Embrace Complexity, Effective Resource Use in a Circular Economy. So why us, Metabolic? Eva's going to tell you a bit more about that as well, but we are a leading sustainability and systems thinking organization. We not only advise business, governments, non-profits, but we also take action. As I said, developing new technologies, developing new ventures and businesses to really help accelerate change. So Eva, I'm going to pass over to her in a second. She has a background in molecular biology and industrial ecology, and she founded Metabolic in 2012 with the mission to transform the global economy to a fundamentally sustainable state. So you're in very good hands in terms of the Disruptive Innovation Festival. Eva's been named as one of the top sustainability influencers in the Netherlands for the past couple of years. So yes, we are based in the Netherlands. We're based here in Amsterdam, but we work internationally from everywhere from Taiwan to the Caribbean, and we're really looking to take this subject to a global path, and we hope that a lot of you will be working with us on that. So without further ado, I will pass you over to Eva.
Thank you. That's great. So as Adam said, it's a great pleasure to be with you guys here today at the DIF Festival. And as he mentioned, the title of of my presentation today is Embrace Complexity, Effective Resource Use in a Circular Economy. It is a kind of advanced talk maybe for some of you, because I will be getting a little bit technical about how we should actually be using materials and thinking about material use in the context of a circular economy. Going deeper than some of the normal, let's say, rhetoric. All right, so I'm just going to introduce Metabolic and also some of the main reasons why we even got involved in the circular economy and the sustainability field as a whole. So as Adam mentioned, I founded Metabolic around 4 years ago in 2012. We are what we sometimes refer to as a systems consulting and clean tech development firm, but really that gets back to what Adam already said, the thinking and knowledge collection as well as the doing and implementation. And our mission is to transition the global economy to a fundamentally sustainable state. We have offices in both Amsterdam and Aruba, and we have a kind of structure with our organization that is a bit like a pipeline. So we have our consulting activities and our consulting division, and what we do there is really try to understand the global system. So we map out different sectors, we collect information on resource flows, we strategize, provide companies with advice on their corporate strategy, etc. Here is a picture of work that we did for one of our clients, CNA, a global fashion company. Then when we find something in this big global system where we actually think that there's potential to intervene and genuinely change something, we formulate our own R&D trajectories and our own development projects. And one of them is actually a project called De Keuvel. So as you can see in this picture, we designed the idea for a closed cycle circular neighborhood, and then we actually we built this neighborhood in Amsterdam together with a group of partners, and including many architects. And finally, when we actually have something that is a really effective technology or a solution that we think can work well, we scale it into a venture of its own. And our first commercial venture, we started it last year. It's called Spectral Utilities. It focuses on delivering integrated software and hardware solutions for the transition of the energy transition, so smart grids and renewable energy. When I started out my career, I actually started working in, when I was quite young, when I was 13, and I was not an environmentalist. This wasn't really something that, that I actually personally was taught to care about. My parents were much more interested in technology and innovation and sort of progress as a whole. But then I ended up at university and I started to encounter more and more really grave societal issues. And this picture that you see here, it's just a snapshot of a lot of the things that we're facing, from droughts to rampant consumption to starvation all around the world. So I was in college, and I was going to be a molecular biologist, so I was growing a lot of bacteria. And this picture that you see here, it shows two flasks. One has just growth medium, and the other one is full of E. coli. And next to it, you see the pathway, the shape of the graph with which the E. coli grow. And this is a typical exponential growth curve. So for a long time, it looks like nothing is happening, and then suddenly, as the cells go from 2 to 4 to 8, the doubling rates increase, and suddenly the flask is full. And within only one sort of generation, the flask goes from being half full to completely full, and there's suddenly no more food. And so I was really used to seeing this particular growth curve, and I understood this inherently from working with these bacteria. And when I ran into these very similar looking exponential growth curves in some other courses of mine in college, I started to get really concerned. Because as you can see here, for pretty much every single parameter that's important for human well-being and human life on this planet, we are on this kind of exponential track. And that's actually, so for pretty much every parameter that's important for human well-being and human life, we're on this kind of exponential track. And if you know anything about nature and natural systems, these are what are called positive feedback loops. And as positive feedback loops, when a positive feedback loop occurs, it basically accelerates its own development. And there's no way for this to stop without some kind of crash in natural systems. So usually a death of a population, etc. So one of the key things about exponential growth is that eventually there's a limit. There's a tipping point that you hit beyond which you can't grow anymore. And with the E. coli, it's pretty straightforward. There's a certain amount of food in their flask, and if they run out of that food, that's when the entire system crashes. But with these exponential curves that I ran into, I had no idea where the actual limits were. And I was wondering, you know, does anyone know? How far can we continue growing on this exponential path before we hit a crash point? And so I was very happy to see that the Stockholm Resilience Center had coordinated this effort to create the Planetary Boundaries Framework, which actually starts to examine exactly that question. Where are those tipping points or places where we really can't cross when moving on these exponential growth curves for all these resources? And as you can see, they've defined 9 key areas, and even though we may talk about climate change the most in the media, climate change has actually been less transgressed than some of the other key boundaries. In particular, biodiversity is one of the most severely crossed planetary boundaries, and recently in the latest WWF Living Planet report, we once again got very somber news that 58% of global biodiversity has been lost in the last 40 years. So if you think about these exponential growth curves and doubling, we're in the last doubling phase. We're in the kind of last round to do something about that particular problem. So all of this sounds pretty grim. We're facing lots of different problems. It's a convergence of crises. We're, you know, overusing resources like water and paper, and losing biodiversity and hitting key sinks on emissions, etc. What exactly do we do to solve this problem? The framework that we've been using with Metabolic that is actually very useful for looking at an approach to solutions in this area is the frame of a circular economy. Over the last 4 years, we've done over 150 projects with various client groups on applying circular economy thinking to things as diverse as sectors, cities, and regional development. And we've gotten a lot of value out of exploring this as a framework for problem solving. It's backwards. So what exactly is the circular economy? Most of you watching this probably know. But to make it really simple, you can define it in contrast to what we currently have, which is a linear economy. So we extract resources, we make products with them, and then we dispose of those products when we're done. This is very much not like what you see in nature. In natural systems, if you enter a forest, there's all sorts of resources cycling, but they're all continuously getting reused and reabsorbed. So if a tree dies, the wood gets eaten by all sorts of insects and detritivores, and then those in turn get eaten by other creatures, so everything is in continuous flux and motion. We have actually not followed that model in designing our own economy, and unfortunately this has led to a certain pattern where we're continuously extracting resources and then ending up with huge amounts of waste. So with Metabolic, we actually wanted to understand this picture a little bit better, and we conducted a study on the total global material flow for the year 2010 to get a picture of what exactly are we extracting, where are these resources going, and which ones are the most significant. We also wanted to see how are these resource flows connected to upstream and downstream impacts. So this quite complex and maybe scary looking diagram is a sand key. So that means that the different lines are scaled to the amount of material that's flowing through. So everything is kind of accurately scaled, except for water. Water is on a logarithmic scale. It would normally be 10 times as large, but that would not fit very well, so we put it on a log scale. And what you can see is that at the very end of the graph, there's two very thin lines. The top one is composting and the second one is recycling. And so those two thin lines, that is what we recover on a yearly basis from all of the resources that we're extracting and putting through the entire system. So this, in short, is the definition of a linear economy. We're not getting these resources back into the system. A lot of them are ending up either dispersed or in long-term stock, but this is also something that gets that I raise a little bit later, because the understanding of how these stocks and flows are working is actually really significant if we're trying to design an economy that can function perpetually on the resources that we have on the planet. Another thing that's really important to note is that different resource flows are actually disproportionately associated with some of the planetary boundary transgressions. So even though biomass and biological material extraction is a pretty small fraction of the total that's been removed, around 20% or so, it's actually responsible for many of the most severe planetary boundary transgressions, like biodiversity loss. So in contrast, obviously that's the picture of the linear economy, extracting a lot and dumping it out. What is the circular economy? So the circular economy has been variously described as an economy that's regenerative and waste-free by design. A lot of the focus on the circular economy is around materials management. The Ellen MacArthur Foundation and McKinsey published a very well-known and well-cited paper in 2011, which documented the huge potential of the circular economy. And the quote here comes from that report, where they basically analyzed that between 340 and 630 billion US dollars per year would be available at the European level if we were capturing instead of wasting those resources that are in our product cycles. So materials do indeed have quite a lot of value. You might not guess it, but an iPhone 5 has $168 of just raw material value in it. So you can imagine how game-changing that would be indeed if a company like Apple was able to get all of that value back. But there's a lot more to the circular economy than just thinking about materials and recycling. In this collage of pictures, here's just a few points to consider about why materials can't be viewed in isolation. So on the top left, we have a small child in a pile of e-waste, and actually a majority of the world's e-waste still ends up illegally exported to developing countries, where it's taken apart by hand over open fires, exposing people to a lot of toxic materials and chemicals that are in the e-waste itself. So in theory, you could have all the value recovered from the iPhone in a sort of perfect recycling model. But if that's the cost, if it's happening at the expense of human health and well-being, then obviously that's not something that we would want to fit into a circular economy. On the bottom left, we have a picture showing, it's a graphic that shows how long we have for the use of lots of different resources. So critical materials, metals mainly, that we're running out of because actually in the past we never used them in certain products like phones, but suddenly with the explosion of these markets, the exponential demand for these types of resources has created resource shortages. And so even if you have perfect recycling, because the volume, the throughput is going up every year, you still have to contend with functional scarcity and shortages of different resources, and you have to consider what this means for different stocks and flows. And then on the top right, we have mine tailings from a mining operation, copper mining operation. And again, this gets to the point that even if you have perfect resource flows, perfect resource management, your extraction processes and your recycling processes can still have a huge amount of environmental damage. And if we're undermining the natural capital, the sort of very basis on which our planet operates, then again, this can't be part of a circular economy. And there are lots of other examples like this that show that really you can't look at materials as an isolated challenge. It's really part of a system. So we have defined these 7 characteristics for what a circular economy should be. So if you actually manage to achieve a circular economy, this is what it should include. The first one is that all materials should be designed to cycle infinitely and at the highest possible value. Then all energy should be based on renewable resources or otherwise sustainable. Biodiversity and natural capital should be structurally supported so that we're not undermining the resource base that we depend on. Likewise, both culture and society and human health and well-being should be supported, so that gets back to the kids and the e-waste. And we should be thinking of generating multiple forms of value, not just money, but also caring about things like aesthetics and happiness, etc. And these are all things that are not currently measured in a lot of the economic models we have. And the system itself, whatever economic system it is, it should be adaptive and resilient. So if changes in circumstance happen, it can actually absorb those and adjust without crashing. And because when the economy crashes, everyone knows that that's not very pleasant. So in short, the definition that we've come up with for a circular economy is that it's a new economic model for addressing human needs and fairly distributing resources without undermining the functioning of the biosphere or crossing any of the planetary boundaries. This might not sound so radical, but it actually is a huge departure from what we currently have. Our current economy does not follow these rules, and it doesn't ascribe to the criteria that we have defined on with our circular economy characteristics. So what we actually need is a real system redesign. There's a picture of a forest here on this slide because that's what I always think of as a model. So if you imagine if you go into a forest and you see how resources are being exchanged, like energy resources or food resources, what are the rules that are governing that among the different creatures living in an ecosystem? That is kind of how we should be imagining designing an economic model for ourselves. Likewise, if you imagine in your body, the currency is maybe oxygen or ATP, the energy carrier in your body. Imagine if you had like a setup of a typical economy where your heart was, extracting sort of telling your lungs that they couldn't have any ATP because they need to pay interest or something like that. It wouldn't really make sense, right? So we have to act as though we're one collective organism, and the economic rules that we create have to match that. But in any case, that could be a whole other topic of conversation. We're here to really talk more about the technical practicalities and to move to this kind of different economy where resource flows are optimized and consider all these different impacts. We actually need a different mindset and a new set of tools. So I've mentioned stocks and flows a few times, and this is kind of a schematic that takes this linear economy picture and explains it a little bit in terms of environmental stocks and flows. We have our environment, which is continuously producing new material reserves, and we have existing environmental stocks. So you can imagine this is something like standing wood or trees in a forest, and that has a certain rate of replenishment. So every year that's getting replenished at a certain frequency. And for many of these environmental stocks, so let's say we're talking about trees, we extract them at a certain rate and they become economic reserves. So then we have wood. And then once that economic reserve gets turned into something like a building, here we've called that an economic stock. And for the most part in the linear economy, there's a little bit of cascading between resources. So for example, wood that's been used in a building and then having it chipped up and used in some other function. But there's still a very high rate of loss, so things end up as waste. Now, if you start to imagine this in a circular model, you actually have the rate of recycling and rate of replenishment balancing the rate of extraction and rate of conversion. And so this is kind of obvious, let's say, but it gets really challenging because for every single resource that we have, whether we're talking about fossil fuels or fish or indeed different types of wood, they have different stock and flow dynamics. And as the population grows, the demands for these resources are increasing exponentially, and there's all these different interactions between the stocks and flows of products. So actually to design or to even get to a circular economy, we face a number of technical challenges of actually being able to recover these resources in a way that will continue to support economic demands and activities. So we're facing two different types of boundaries. One of them is that we have limits on sources. So this is the same graphic that I showed before, that we are running out of certain types of metals and minerals. And this is the case for quite some resources that we, especially biological ones that don't get replenished at a very high rate, we can't extract more than what's available. Then we have a different kind of boundary constraint, which is called a sink boundary constraint, and that has to do with what the Earth can absorb in terms of pollution and impacts that we put out into the world. So for example, CO2 emissions. This means that even if you have a ton of fossil fuels, like oil, you actually have a sink constraint because you can't burn all of it without creating all sorts of planetary boundary transgressions and problems. So what this actually translates to is that we need, in order to achieve a circular economy, we need to start having a much better understanding of what our planetary budgets are. So we need to know where we are along the growth, this exponential growth curve, and how close we are to some kind of unsafe tipping point. And we need to make sure that we stay in that safe operating space. And that is getting, people have a better understanding of that on a high level with the planetary boundaries, for example, even though that is also a contentious, that's something that's getting worked out further. But it's very difficult to get this to be translated to day-to-day actions. So if you run a company and you need to buy a bunch of wood, how do you relate that to whether that's crossing a planetary boundary? Or if you're going to design a new product, how do you make sure that you're not actually overusing a scarce resource, or a resource that's going to be scarce in a couple of years, because you don't really have these insights. There's a big disconnect between the high-level knowledge that we have about global dynamics and the day-to-day decision-making that needs to be made by people who are actually building the economy and therefore making it circular or not. So that's where it gets to. So in this budgets graphic, you can see we have already used and committed a lot of different resources. And so this is just kind of an example. These are fake numbers. These are not real numbers. And then we have system limits, which are defined by the sinks in many cases. So even though we have more oil, we can't use it, or even though there's more fresh water, we need to leave it for other creatures. So we need to actually make sure that we're continuously in that operating space, and that we actually manage to stay there while designing a system that is satisfying our own needs and circulating resources fairly, not just for our generation, but for many generations to come. So we talk about the circular economy a lot, but actually, if you really take a look at what the economy probably looks like, it's a lot more complicated than that. So the picture that's on this slide is a snapshot of the human metabolism, and it's a high-level abstract picture of the human metabolism, but you can see that there's tons of interactions, and ultimately the way the human metabolism is designed, and most ecosystems are designed, is circular. It's what we're trying to strive for with our economy at large, but it's definitely not in a single straight line. There's all sorts of exchanges and loops and pathways, and it's a very complex system. And what this system works on, and it still manages to fit these circular criteria, and that's because there are very smart rules that are embedded into how the system works to make sure that it ends up with the right outcomes. That you're not overusing resources in your body, that you're continuously supplied with energy, and you're not producing toxic waste, etc. Like you never would, but you would die if that happened. So anyway, so this is kind of like the model that we're facing. We have this very complex economy. We have these sources and sinks, and we need to stick within these key budgets in order to actually achieve this circular economy vision. And we actually do need different kinds of tools to start doing that. And that's what this the rest of my presentation is going to focus on. It's how do we start thinking about resource use within this context. So in the circular economy world, and also in Cradle to Cradle, and in a lot of these schools of thought, it's very common to talk about biological and technical cycles. I'm sure most of you have heard this, and also this very well-known diagram that we have from the Ellen MacArthur Foundation and McKinsey. It shows basically the division between biological and technical resource use. So on the left hand you have biological, and on the right you have technical. And the idea is that you have these resources on the left going into different types of treatments like composting or biogas production than the ones on the right, which are mostly focused on refurbishment, recovery, recycling. So one of the things that we argue is that this division isn't, it's a good, let's say, theoretical starting point, but it's not enough to really make the right decisions for moving towards circularity. For one reason is that the distinction between biological and technical resources is pretty ambiguous, and it's also not the right piece of information that you need when you're making decisions about what to buy or how to use it or how to design something. So we need actually more sophisticated tools for this. So I said that the description between these two things, the distinction between biological and technical materials is ambiguous. And just as a small case in point, here we have two materials. We have paper and we have oil, crude oil. And normally they fall into biological for paper and technical for crude oil in terms of their overall distinctions. But you can see how ambiguous that actually is, because oil, as most of you know, has actually been made from different biological materials that have been compressed under huge amounts of pressure over millennia. And paper, the way that we use it nowadays, it's highly processed biological material with a lot of different additives and chemicals, etc. And at that point, is it a fully natural material or not? And so actually what the recommendation is within these fields in terms of design is that you're actually supposed to aim to keep biological and technical materials separated. So when you're designing a product, you keep your biological materials in one area and your technical materials in another, and then it's all good because you can compost everything biological and you can recycle everything technical. But actually, you get into a lot of issues with that. So here I just showed, okay, so if we don't want to process wood anymore and we don't want to use all sorts of technical materials to enhance its functionality, we might as well write on wood, I guess, you know. And that's actually not what we want to get to, because the functionality of these products and the way that they work in the economy is actually critical for maintaining a certain level of performance and optimization. And there's actually no need, if you start to think about this in more detail, to be that strict or Puritan about this separation between biological and technical. For one thing, the main point of the separation principle is to be able to actually safely dispose of these materials into the environment, or keep them cycling without problems. But actually, it's not really a problem if you dispose of something in the environment as long as it's not hazardous, toxic, corrosive, or has byproducts of concern when it degrades. And these are not always related to something being biological or not biological. So you can actually have, imagine huge amounts of sewage or wastewater. That's fully biological, but you still don't want to put that into your environment because that starts to create lots of problems. So there's correlations in some cases as a shorthand, but that's not really the main point. So the arbitrary separation of biological and technical resources in design presents a really large and unnecessary design constraint. There are other ways to get around this that can help really get to the root of the problem. And that's, in finding this kind of continuous issue coming up, we started to develop what we called the material circularity factors. So we thought about, okay, so what are the real main criteria for which you would decide whether or not to use a material in a certain way or not. And we came up with around 14, so these are some of the circularity factors. This is an illustration to show how this works. So for factors like hazard or renewability or recyclability or scarcity, for each of these parameters, we score a material from 0 to 100. So they all get a score on each indicator. And then there are some compound indicators that we've defined. So recycling priority, material risk, and scarcity risk that allow you to actually understand it in a glance how that material should be used in certain contexts. So just to give a quick example, if a material is really scarce, is in high competing demand, so it's used by the market in lots of different functions and has no available substitutes, then it's a really important thing to recycle. So if you're designing a product and you're going to use that material, you really have to make sure that you've designed it to be fully recoverable. For material risk, if something is poisonous or hazardous and doesn't degrade well in the environment, you definitely don't want to put that into a product that's going to end up in the environment. So this is pretty logical, right? You have these different sort of guidelines. And again, this is not at all correlated very well with it's not correlated very well with the division between biological and technical, because you can imagine, as on this next page, you have mahogany, which is a kind of wood, and pine, which is also a kind of wood, but they have very different characteristics. Mahogany is a tropical hardwood. It grows very slowly in very few habitats. Pine grows like a weed in many, many places. So you wouldn't treat these like the same kind of material. You wouldn't use it for the same functions, and you wouldn't prioritize it in the same way in a circular economy. So we have kind of example scoring. So for mahogany, you have a slightly higher recycling priority, and the scarcity risk is higher. For both of the wood, the material risk is pretty low. And then for these elements, antimony, iron, and arsenic, you have very different profiles. So antimony is extremely scarce. It has a very high recycling priority. It's actually one of the more, it's a critical material. Iron and arsenic are less scarce, but still non-renewable. So it's also important to get those recycled. But they have very different material risk profiles. Arsenic is obviously a poison. So you want to make sure that you have a different way of thinking about how to use that in the economy itself. So these are this is an illustration of how having this more fine-grained approach to the properties of materials helps think about how you can actually deploy them in a circular economy. So once you have this understanding of materials and a kind of a database of all the materials scored on these factors, you can start to think about how to match materials to different types of products. And so we've defined a few different categories. We have products that are consumable. So you have disposable products. You have products that are dispersible, that are meant to go into the environment, like paints or chemicals. And you have non-consumable products that are either simple or complex, and they have different timelines associated with them. So under simple here we have like a sock and a chair, and complex we have electronics and cars. And then there's infrastructural products that have different properties as well, so depending on their recoverability. So what these circularity factors and the scores allow you to start doing is coming up with some logical shortcuts for why would you use this material in a certain way. So as you can see, mahogany is much better, or is quite an appropriate thing to use for a very heirloom piece of furniture, and pine is much more appropriate to use as a pallet, but you wouldn't really want to switch this, because using a very slow-growing, scarce wood to create disposable pallets would be slightly heinous. So anyway, so here imagine, okay, we're designing dispersible products, so products that are designed to go into the environment. And actually it's pretty interesting, around 40% of all the materials that go through our economy are actually structurally dispersed or consumed. So this is again, like through our analysis we were able to find that, okay, if you really want to achieve a circular economy, first of all, that's a big problem. You're never going to have it fully circular if that's part of the deal. Of course, a big part of that includes food, feed, and fuel. And these are materials that are always going to be dispersed and have to be brought back in other ways through nutrients or resources. But it also includes around 20% of all the chemicals that we produce, and an estimated 0.5% of metals. So you have paint, you have 5 minutes? Yeah. So you have paint, you have pesticides, you have brake discs, etc. So the highest priority features for materials that are ending up in the environment as dispersible products is that they have to be non-toxic, they have to be biodegradable, and they can't be scarce or in competing demand. So another thing, of course, is with circularity and the design approach, ideally we would avoid creating dispersible products altogether. If you have to, then you want to make sure that they have those properties. But if you, ideally, you would actually want products that avoid that. So here are two cool examples that I really like. So one of them is Morphotex fabric. As you guys might know, butterflies and birds have really highly pigmented feathers and wings, but they don't use any, sorry, they're not pigmented, they're highly colorful, but they don't use any pigments. So there's no chemicals producing that. All of that color is produced through the nanostructure of the material, of the feather or of the wing. And that's what this group did with Morphotex fabric. So they've tried to imitate that to create a blue color without any chemicals. And on the right you have gecko skin. So you can see a 4 by 4 inch piece of this material holding 300 pounds. And it's designed using the same principles as gecko feet. So geckos have very highly, let's say, well, they're not perforated, but they just have a very high surface area on their toes, and through the interaction, the molecular interaction between their toes, they're able to walk on walls. So some scientists thought, well, why don't we do that for adhesive? And then there you go, you don't need glue anymore. So this is a way to structurally design out dispersible products in a circular economy. For disposables, actually, there's a lot of focus on disposables and short cycle products and talking about the circular economy, but only around 1.5% of all materials are ending up in these short cycles of 1 to 2 years. And there are, again, some ideal guidelines for what to do with that. Ideally, you have renewable materials that are actually going to biodegrade again and are non-toxic, etc. So quite similar to dispersibles, but because there's so few of these, you can also use materials that are renewable. you think very differently about designing for long-term use. So for example, infrastructure, cars, and bridges, etc. Most of our material, well, almost half of the material is going into long-term stock. And what that means is actually that we really don't want to lock up very critical materials that are needed for multiple functions into these types of long-term stock. So the highest priority features here are that the materials shouldn't be scarce or in high competing demand. They should be 100% recyclable and have a low depletion rate. And so this is something to consider. This is a very beautiful temple in India. It's made of gold. We shouldn't do this anymore. It's great that this happened at some point in history, but it's actually not a very good use for our materials at this point. And with these types of circularity indicators, you can actually point to that and say, this is not the right use for this material. It should be prioritized elsewhere. And finally, going a level deeper, once you have matched materials with products, you can match products with business models and how those should be ideally deployed. I'm just going to give one example here. Leasing is given as a sort of primary circular economy business model. And that, I think, requires some caveats, because in some cases it's really a great model and a great idea, and in other cases less so. So here we have two cases. We have Mud Jeans. It's a Dutch company that is leasing pants. And then on the right we have a company called Bundles, another Dutch company, and it's leasing high-end, super efficient washing machines. So I think you might have a gut feeling about why this makes sense or doesn't make sense, but if you imagine a very complex product that requires specialized disassembly and recovery and has a lot of high-value materials, like the washing machine, that's actually an ideal product for leasing. And that also means that people can, it's an energy-using product, so people can upgrade to the latest version and make sure that the functioning of their house is actually at the highest efficiency possible. Pants, on the other hand, jeans, they're made of a uniform textile. They're actually much better suited to putting into centralized recycling pathways. And there's less incentive, let's say, to put pressure on the designers or producers to pick very specific design processes or components, because they're so much more uniform. So there's a certain kind of cutoff. You could still argue that there's benefits from leasing, but the reverse logistics of the sort of like returning of those pants probably outweigh, in terms of the energy demand and the complexity around that, outweigh the value of that specialized leasing system. So again, this kind of way of thinking about this can give insight on how to adjust your business model as well. So the whole point of this framework is to provide logical shortcuts that help you process the complexity of the economy. So we understand where we want to go. We understand we want to go to a model where we are cycling resources in the right way within these planetary boundaries in a safe operating space and making the best decisions about how to use these resources. But it's too much information to deal with on a daily basis. And that's why having these types of scores and these types of ways of thinking, of prioritizing, can help actually decide where you want to, how you should design or how you should allocate different types of values. The important thing about this also is that we've designed it to be dynamic. So for example, if a scarcity score changes, or if recyclability changes from one year to the next, the actual score for each product should change. So here's an example. I recently was a jury member at the Accenture Innovation Awards, and the winner of the circular economy category was a company called Ionica, which is using magnetic fluid to actually recycle PET and decolorize it. So it's actually a really interesting technology, and this could change the face of plastics recycling. So if we start to get new technologies, then the actual scores for recyclability for different materials would change, and that means that your decision making around how you would optimally deploy certain resources has to change as well. It's not a static thing, it's a dynamic, evolving landscape. So going back to this graphic about where to start, we really wanted to understand, okay, so where are the priorities? If we have limited resources and limited time on our hands, where should we actually focus on the diverting resource flows and changing the way that people are interacting with them? And we identified this sort of primary list of areas where there's very big circularity gaps or huge amounts of materials getting lost or very high impacts on the upstream side, like with agriculture, which is resulting in so much biodiversity loss. So we have this primary area list for interventions, but this work that we've just presented is actually at a pretty early stage. We've been thinking about this ourselves. We've been trying to develop these types of frameworks, and we see the value and the need for doing this. But at the same time, we need partners, we need companies to pilot this with, we need designers to work with. We really want to take these ideas and test them out and take them further. And that's actually the kind of call that we have to everyone in the audience here. If you do see the value in this approach and having these logical shortcuts for moving towards a circular economy, reach out to us and let's see if we can actually figure out how to take these frameworks and actually build them out into tools that can be used by everyone, not just by us in our advisory practice. Anyway, thank you all for your attention, and I look forward to the questions that were collected in advance.
Yeah, thank you. I've upgraded to a much more complex microphone now. I'm embracing complexity. And so first of all, thank you very much for giving a really clear overview of the circular economy and material flows. And for me, one of the big takeaways actually was this idea that just because we have to operate within this complex space and that we should embrace complexity, that our ideas don't necessarily and our actions don't necessarily need to be complex. There's actually quite a lot of simple things that we can do, and there's stuff that we can be working on immediately. One thing that you mentioned a few times actually was design, and there's a lot of talk about how we can design in for the future to change these things. We actually had a question in advance from a product designer who wanted to know exactly, could you give any specific examples of what someone in their position should be thinking of when they start designing a product from scratch, knowing that what they know now?
Yeah, so I mean there's certain guidelines that you would apply to the process of product design. The first one would be really it's at the level of defining the function of the product. So does it need to exist at all? And is there a way to provide that function in unexpected ways? So you always look at the intention, and usually the systemic effect of a product is going to be the largest. It doesn't matter. So to give an example, the hugest impact of a car is the fact that suddenly you've given someone the ability to move around and consume huge amounts of fuel doing so. And that has a systemic effect on infrastructure, et cetera. So designers should really think about first of all, the systemic effect of their choice, of the product that they're trying to bring into reality. Secondly, if it's determined that that's going to be a positive or necessary systemic effect, then think about reducing the material footprint, so any sort of dematerialization options. And then finally, there's a lot of these types of practical guidelines. So, okay, where is it going to be used? If it's going to be a dispersible product put out into the environment, then the guidelines that I gave for making sure that it's non-toxic, that it's biodegradable, et cetera, those are critical. And these shouldn't even be optional. This should be like, okay, if you're designing a product that goes into the environment, it should be non-toxic and biodegradable. And likewise with the other sort of categories. So what we really would like is actually to put out a simple sort of manual or guideline that could outline this for designers.
Okay, good. And so I suspect that there probably are some designers making some headway, and you mentioned there's quite a few other categories. Is there anyone in your mind who's actually leading on this as a whole, bringing it all together at the moment?
I mean, I think there's some companies that are doing really great stuff. We've worked with Interface in the past and with Deso, so these are carpet companies, and they're with their particular product portfolio, carpeting, they're really trying to push the boundaries. But I think in terms of holistically applying all of these things and really thinking about it from this bird's eye view and how you would actually cascade resources and deal with stocks and flows over decades, I don't think that there are many companies that are really doing that. And I think that that level of discourse, it would be great to actually bring up with these market leaders.
Okay, good, thank you. We're actually talking here in Decoval, and if you don't know about Decoval, please do check it out online. It's one of the most sustainable neighborhoods in Europe, which Metabolic helped to establish. And a lot of the circular economy is applied at that kind of like, well, here it's a community, but also we work across regions with governments. So how does this idea and this thinking about how we can embrace complexity with resources apply itself to that kind of more macro picture?
Yeah, it's actually really interesting. We've been taking the same thinking and applying it on a spatial scale as well. Because of course, when you think about how resources should optimally be managed in a city context, you wouldn't think of closing all resource cycles within a city like Amsterdam. It doesn't make sense for Amsterdam to recycle all of its electronics and all of its textiles, etc. But then you think about, okay, on what level do you close which resource flows? And so the ones that are most ubiquitous, like water and energy, you want to close on the smallest cycles. And then when they get more complex, then you have larger cycles. So for certain really specialized materials, maybe there's really a few global locations where they're optimally recycled because or recovered, because that requires such high levels of infrastructure investment. So it's a big question about the levels of centralization and decentralization. So we've been trying to incorporate that type of thinking into advice for how to develop regional circular hubs and design cities to be circular, and also advising on where you should really strive for self-sufficiency versus collaboration with other regions.
Okay. There might be a bit of crossover then into my last question actually, which is about the Internet of Things, and someone who actually wrote to us again in advance and wants to know what is the role of the Internet of Things in helping to realize the vision that you've outlined?
I think there's a potentially huge role, although it's a little early to say how that's going to play out. But as you can see with this type of level of complexity of materials in our economy, one of the things that would be really beneficial is to have products that are actually tagged that identify what materials are in them, so that when they're disposed of, they can be automatically scanned and the materials can be taken apart and used in the best way possible. And so this kind of insight and real-time knowledge about where our resources are, where they're going and how they should be routed, it would bring huge amounts of benefit to being able to realize a genuinely circular economy. We've done a project on electronics and kind of creating a concept for this sort of resource tagging and tracking tool for a smart meter, and we got to explore some of that thinking there, and I think it would be game-changing, but it also requires whole new sets of technologies to be implemented and waste collection and processing to completely transform from what it looks like now.
Okay, thank you. Well, hopefully more to come very soon. I'm just going to ask if I've got any time for questions from the audience.
Yeah, I'm looking at the time. I think we have time for one more question. My question would be that in terms of policymakers, I mean, there's been a lot of talk about taxing resources instead of labor and lots of different types of policy ideas that go around. What would your advice be for policymakers that really want to make some steps towards implementing this approach? What should they be thinking about? What should they be doing first?
Okay, I'm just going to re-speak that question because we didn't have a microphone back there, but what would be your advice for policymakers for how they can actually kind of drive action and actually make these things happen?
Well, one of the best tools that policymakers have is actually the fact that governments are huge buyers of resources. They buy infrastructure, they buy buildings, they have lots of different offices, etc., where they actually, well, they purchase computers and products. So through creating guidelines for procurement or policies that actually start to require this more sophisticated approach towards material management in their own material chains, they can start to have a really huge trickle-down effect that is then adopted in other parts of the industry. And I think that that's one way that they could really have an effect that's very practical. The other thing is that, of course, a lot of the things that I've mentioned here, like products that are dispersible and designed to go into the environment, should not be toxic or bioaccumulative, etc., those lend themselves to regulation pretty easily. You could say, okay, these logical rules, we can just codify them as law. I know that that would have a huge amount of pushback, and probably justly so, because it's a huge step to make for industry to move from where we are now to that point. But I think acknowledging that it's desirable and then creating a stepped plan for that might be a very logical thing to do.
Okay, thanks very much, Eva. So thank you very much for the time to outline what we've talked about today. I hope that a lot of people watching at home have really got to grips with what we're talking about here, and hope to hear from a lot of people and work with them on this incredibly interesting but complex idea. So thanks very much for watching. Please do join us online, join us on our website, Twitter, Facebook, LinkedIn, and just tell us what you think, but really join us in discussing this and work with us to take this to the next level, and we look forward to working with you.
Yeah, thanks a lot. Thank you, everyone.